Right. All right. So we missed Monday. I think today we'll go over the AdaBoost algorithm and some of the stuff on the decision trees. Actually, the last part of this paper where they do this cascading tree classifier, you don't actually need to do that. I sort of added it on the end, just sort of good to know type thing. And Justin's who's super ambitious, maybe he'll end up doing that for this one. Who knows? But it's there, and I want to talk a little bit. Sometime I'll have a chance to talk a little bit about decision trees, but I personally don't find them super useful. But whatever, we'll go over them and introduce them at least. Yes?
Are we all that's left?
No, I think they're just not coming, or I don't know. I mean, there's always been numerous people that don't come to class.
Okay, I was just making sure.
I don't know, maybe they just wait for the recordings, or I don't know. Maybe they still have a sweet gum tree and laying over their driveway, or who knows.
It's just weird only seeing them.
Yeah, there's not very many. So last time, let's see, do I have that open? No, I don't think I do. Last time we went over pretty heavily the features and the weak classifier. So you're going to have lots and lots of these classifiers, HJ, okay, where they're going to either say it's a face or it's not a face with a 0. Okay, depending on whether the feature value is less than or greater than, depending on the parity, the threshold theta. And we talked about how before you do anything, you're going to go through and find what is the best level of a threshold on all of the training data. And that is going to be something that's not going to change during the AdaBoost algorithm. You're going to find the optimal thetas given the training data that you're going to use, and that's going to be set. The weak classifiers are not going to change then. Okay? Then we need to work on putting together the weak classifiers into a strong classifier. Okay? And the idea of that is with an ensemble of where you're going to combine together many weak classifiers to sort of have a vote. The different weak classifiers are going to vote. And so, as a very simple way, I've given you this mathematical representation that is basically just a majority vote. This is a fancy way of writing a majority vote. Okay? So if we talk about a classifier, I don't know, why is there a subscript? Oh yeah, T, okay. So we're going to have big T, total number of classifiers, okay? And we're going to loop through each of those big T classifiers to each individual weak classifier HT, okay? And for any given image X, we're going to sum together all of the classifications. We're going to divide by the total number of the classifications. That's going to give the average vote. And if that's greater than 1/2, if more than half of them voted for a face, then it's going to be a face. If less than half of them voted for a face, it's going to be a non-face. So this is just simply majority vote. I can say it's just a majority vote of T weak classifiers, but I wrote the mathematics here because it's going to help us understand the one that we're actually going to use. I put an H star here to say, well, it's like the one we're going to use, but it's not the one we're going to use. Instead, we're going to use this h of x, which you look at the equation and it's very similar, and it's actually rearranged a little bit from the equation that's in the paper. They multiply both sides by that denominator so that there's no fraction. But it's the same exact equation, just in a different form of what's in the paper. And the only difference between this one and H star is that it's a weighted average. Okay, so different classifiers get more votes than others. Okay, so in the election for the president, California gets more electoral votes than Rhode Island does. Okay, so California's vote counts more than someone else's vote, and that's the same thing we're doing here. Is that different ones of these weak classifiers are going to have different strengths of their voting. So that's the main piece that makes this a little bit different than just a majority vote. Now, the question is, how do we first of all, how do we determine which of those 180,000 classifiers are going to be in this big T number of classifiers? Now, we haven't said yet how many big T is. Okay, I think when I did it, maybe I had 20 or something like that. Okay, in the paper they said they used 2,000 total number of features. That's in all the cascade. Okay, but it's not going to be a very large number, this T. Okay, so we need to find out of this 180,000 features, how do we choose 20 or 100 or 200 of them? Okay, which ones do we choose? And what weights do we give to these classifiers? What are the alpha values for each of them? So you'll notice that for every HT, little t, that is part of the strong classifier, there's a corresponding alpha t for its weight. Okay? So that's the primary goal of the AdaBoost algorithm, is to pick the weak classifiers and set what their weights are. Okay? So the idea here is, at least to start with, you go ahead and pick what is the weak classifier that has the best classification, just straight up. And you'll notice that the way that the weights are set, both in the paper, and I've written that in the example code that I gave you, okay, is that it just divides by the total number of faces or non-faces. So basically, if you have 50 faces and 50 non-faces, all the weights are going to be exactly equal. If you have 100 faces and 50 non-faces, the weights of the face ones are going to be more because there's more of them. Okay. Also, one of the things we do is that we normalize these weights so that they end up summing to 1. Okay, sort of like a probability distribution type thing. Okay, so that's one thing, we keep them normalized so they sum to 1. But if there's more faces, then the ones that then the weights for the face ones are going to be higher. But I've already done that initialization for you. Okay. So it starts off all things equal, basically. And so then you would obviously pick which is the weak classifier that is the best classification, all things equal. And that's going to be little t equal 1. Okay? Then, what is the really unique thing, the interesting thing about AdaBoost is it says, okay, let's go ahead and update the weights for the next time. They're not going to be everything equal. And what's going to happen is that the weights of the thing of the images that are the weights hold on. Now I'm getting confused. Going to be confusing you. Okay. So, I take that back. All right. So, I'm sorry. Yes, alpha, each weak classifier has an alpha that says how much its vote is. And indeed, AdaBoost will be updating what those are. Okay? And they are a weighted average. There's another weight, and I'm sorry, I confused you. There's another weight that is each image has its own weight. Okay? So, the way we're going to judge whether a classifier, a Jth weak classifier is good, is by saying how much does its classification differ from its actual ground truth value. Yi is ground truth. Hj of xi is what is the Jth classifier's guess for what the xi image is. Okay? So the difference between them is its error. We're going to take an absolute value so that we don't get negatives. We just get, 1/2 or, 1. It's either going to be 1 or 0 because the h's and the y's can only be 1 or 0. So it's either going to be 0, did I get it correct? Or 1, did I get it wrong? This is an error measurement. Okay? And I take the absolute value just so there's no negative ones. Okay? And then each image has a weight. So each classifier is going to have a weight, and that's separate from each image's weight. Okay? And each image's weight starts off all things equal, like I said. Okay? And so in the very first time we're going to when we evaluate this, those weights are all things equal. And so we're going to calculate the error for all of the 180,000 different features. And we're going to pick the one that has the lowest EJ. Okay? With weights for each image, all things equal. Then we're going to update the weights, and that's what this equation here says. At the t plus 1th time step, it's going to take the old weight times this really cryptic thing, beta times 1 to minus EI. Okay? Now, it's cryptic in the equation, but it's really simple. Okay? So the weights for every image start off equal. And then any image that is correctly classified by that classifier should have its weight decreased, because the classifier already is doing them correctly. The images that are incorrectly classified, their weights need to stay high. And any image that's correctly classified, its weight should come down, so that the next time we apply this equation, the weights will emphasize the ones that are wrong. So the next time I choose a classifier, it's going to be the classifier is going to be chosen for getting right the ones that were gotten wrong by the last guy. So the first guy votes, and he says, these things are faces, those are non-faces. The next guy comes in and says, hey, but you got those ones wrong. I do a better job at getting the ones you got wrong. Okay? So every step it's going to update all of the weights for all these images for how strong, so that the images that are incorrectly calculated get more strength in the error measurement. Okay? And so I added this figure here. The top figure is for how the weights for each individual image gets updated. Okay, and I'll talk about the one down on the bottom in a second. So, this beta raised to the 1 minus EI power. Okay, now what EI is for that image. So remember, I represents an image. This is where it gets confusing. We need to understand all the subscripts. We got J that represents a weak classifier. We've got I that represents a training image, and we have T that represents a selected weak classifier that's part of the strong classifier. Okay, so the EI, that was the ith image correctly classified in this step or not? Okay, and these are error measurements. So 0 is that it was correct, and 1 is that it was incorrect. So 1 minus EI is basically saying, was it correct or was it incorrect? So I'm either going to raise to a 0 power, or I'm going to raise to a 1 power. And if I raise to a 0 power, no matter what beta is, that is going to be 1. And if I raise to a 0 power, beta doesn't change. Okay? So basically, if that image is incorrect, EI is 1, so 1 minus 1 is 0, so beta to the 0 is 1. So no matter what, that image's weight is not going to change. Okay? So if that image was incorrectly classified in that step, the next step's weight will not be changed. If that image is correct, the blue line, then it will be decreased. Now, how much will it be decreased? Okay? And we're going to ask, what is epsilon t? And epsilon t, the t there is the tth iteration in the AdaBoost. It's which the t represent. Epsilon t is the error in the best weak classifier. The best weak classifier gets selected, and that's what the t represents. So epsilon t, that is what is the error in the best one in that case, and that's what's determining whether the images are correct or incorrect, is that classifier. Okay, so if epsilon t is 0, that means that every image was correctly selected. Okay, so if every image is correctly selected, then all of the weights, actually for all of them, will get set to 0, because I've already got all the images right. There's no need to do anything more because that thing got every image right. So all the weights are going to be decreased to 0 so that nothing's going to change later on. Okay? The other almost extreme is when the error is 0.5. That's 50% classification. But now remember, this epsilon is a weighted average. So it's not really half of them are right and half of them are wrong. It's that the weighted average. So it actually is possible to have an error higher than 0.5 even for a weak classifier. The weak classifier has to have an overall classification better than 50%, but once it gets weighted, it is possible that it could be worse than 50%, but it's hardly likely because you're choosing the best one out of all of them. So essentially, it's never going to be over 50%, but if it were 50%, then the weights would not change. So if your classifier was the best one, and it's just half the time it's right, half the time it's wrong, all the weights should stay the same because you didn't really get any right anyway. You're just as good as chance. So if the selected classifier is only as good as chance, then the weights should all stay the same, whether it was correct, whether the image was correct or not, because that classifier is not very good. And then you have this sliding scale in between. Okay? So the better that classifier is, the more its correct images decrease in weight. So if I have a very good classifier, all the correct images have their weights reduced a lot, and all the incorrects stay the same. Okay? So intuitively, it makes sense. Whatever you got right, you de-emphasize. Whatever you got wrong, you emphasize. That's all these equations are telling us. Okay? So the top figure here is saying how much the weights get changed for the next iteration. The bottom figure is, okay, this guy got selected. How much should we give, how strong of a vote should we give him? Okay? And if he only got half of them right and half of them non-right in a weighted sense, he should have no vote. He's no better than chance. Okay? So he gets a 0 weight for his alpha. Okay? If he has everything right, then there's no need to go on. He's the best. We actually give him an infinite weight. Okay? So if he has everything exactly right, well, damn it, he's the best there ever is. He got everything right. So we give him an infinite weight. Now, of course, he's never going to get everything right. These are weak classifiers. So it's never going to be infinite, but I had to cut it off somewhere there. Okay? So this is telling how much the weights should update. Ones that were incorrectly classified need to have stronger weight. And this is how much should we believe that one guy that just got picked, depending on how good he is. Okay? And so just these two simple things. If you're good, you get stronger weight. And if whatever images you got bad need to be looked at more closely next time. Those two very simple, intuitive things take these ridiculously poor, weak classifiers and combine them together and get you something amazing. Strong classifier. So it's pretty amazing. I mean, I was really impressed when I went through this and did it. Okay? A little bit, I want to emphasize again the notation here. Let's go back over the equations. Okay? So this is the strong classifier. Okay, there's going to be big T strong classifiers, and that's going to be your main loop. Okay, the main. Let me go ahead and open that up. Face detection, template, train classifier. Okay, so this is the main loop for AdaBoost. Okay? And you notice I made it to be a while loop. I didn't put it as a for loop. At least the way I did it was I wasn't going to set how many classifiers I got. I wanted to set some criteria for, I wanted to keep adding classifiers until I got to a certain criteria. Okay, so you can do something like looking at, well, what's the overall performance of the strong classifier? I want to make sure that the false positives are a certain small amount. I want to make sure, you can set that up. Okay? And so let's talk a little bit about that, the idea of a detection and a false positive, okay? And so oftentimes, we've set up these errors, and we've got this weighted average error that, if you were correct, it counts the same as if you were incorrect, okay? Now, that makes sense mathematically, everything's fair, but it depends. In actual operation, it depends on what sort of trade-offs you have. Okay, so if there's something out there, say we're trying to detect faces, and let's say there's an image, and let's say there's 10 faces in there, and your algorithm finds 8 of them, but misses 2 of them. Okay, so you have an 80% what's called detection rate. That 8 of them you got, 2 you missed. Okay, now you may have falsely said that something that wasn't a face is a face. So there may have been 3 places in the image that you said were a face but aren't. Okay? Those don't play into this detection rate. The detection rate just looks at what things that are faces and how many did you get. And then the false positive rate says, well, how many things did you say were, how many false positives were there in that image? Well, there were 3 things, or there were 4, or whatever. Okay? And that's looking at the image overall. You can also look at false positives as how many things that were not faces did you say were faces? Okay? So, I don't know. Say you're Facebook and you're wanting to roll out a face detection algorithm. Okay? You have to make a choice on designing this algorithm. Are you going to choose something that if it says it's a face, it is always a face and never not a face? Okay? And if you do that, you're probably going to end up where there's many things that are faces that aren't detected. Okay? So you could, and that's sort of a marketing decision. How bad would it be if you ended up with an image and there's, a TV and it says that the TV is a face when there's not a face on the TV? Okay? That might reflect very poorly on you. So you might be emphasizing, I really need to make sure that I have very few false positives or no false positives. Okay? And it's almost always this sort of trade-off that as the detection rate goes up, you get a higher percentage of getting the faces right. You almost always end up increasing how many non-faces you say are faces. It's almost always this trade-off. That the detection rate might be high, but you're going to have a high false positive as well. I mean, that's basically if you say every image is a face, you're never going to miss a face. But you're going to have lots of false positives. Yes?
I guess the false positives would be kind of like paralinear stuff. I don't think I'm pronouncing that correctly, but it's just objects that look kind of like a face, like the wall socket.
Right. Yes, so you could have that. I mean, and sometimes it might even it might not even be so much might not even be that. I mean, if you look at my, my result here, I don't know, one of these guys, one of these windows is like only like the top part of my forehead or something. Okay? And yeah, it's part of a face, but not really, so it all sort of just depends. But you're right, you can get things that look like faces that, might be false positives, or might just have the same texture as a face, So it all sort of just depends.
I got a question. When we're building our classifiers, the biggest they can be is 19 by 19.
Correct.
It looks like on yours you have some that are bigger than 19 by 19.
Yes. And I'll get to that when we talk about the sliding window search. Cool. Good point. That is the topic for today. Okay? All right. So, here's our loop. And I forget what I did. I did something like, the overall classification has to be a certain amount and the false negative needs to... I don't even remember what I put. But I had it keep looping until I could get... the criteria, and I keep adding more and more features until I got what I wanted. So somewhere in there I had a true equals something, and it was either true Boolean, true or false, depending on whether my criteria were met. And it would keep looping through more and more t's, little t's. Okay? And so one of the steps that you're going to, and if you look at table 1 in this paper, Okay. We're basically doing what's here in table 1. It's in this loop. They have 4t. I just have a while loop instead of a for loop because I'm not predetermining how many t's there are. The first thing you need to do is normalize the weights. So you take all of your weights and you divide by the sum of all the weights, basically. Okay, to make them sum to 1. Okay? Then for each feature, oh, that's wrong. You don't want to optimize the theta. That was an old thing. I should change that. Okay? For each feature, you're not going to optimize it. So that was something I had wrong when I was first doing it. You optimize it once in the beginning, and then you leave them there. Okay? For each feature, you're going to calculate epsilon j. Okay? Let's see. Let's remind us what epsilon j is. Okay? Epsilon j is the error measurement for the jth feature. So I'm going to check. I'm going to predict each of the images, check it with its ground truth, and multiply by its weight. And then I'm going to sum over all of the images, and I'm going to get an error measurement, a weighted error measurement for each of the j features, all of them. Okay? Then, whichever one of those has the lowest epsilon j, that will become h sub little t for that particular t. That's the chosen one. Okay? So you calculate all of the errors for each of the features, and then you pick the one with the lowest epsilon j, and that becomes h of t. Okay? Then we need to update the weights. Okay? And the way you update the weights is with this guy here. I need to know how good was epsilon t, that one with the lowest epsilon j. I need to know that. How small was it? And each image, was it correct or was it incorrect? Okay? And that's going to update the weights. That's how the weights are going to be updated. Okay? With beta. And there's an equation for beta, but it's straightforward. You just need it depends on epsilon. Okay? And it's in the paper. So you calculate beta, you know what EI is, and you update each of the weights. Okay? And then, of course, you need to add the winning weak classifier to the strong classifiers list. Okay? Because remember, we have a weak list, all 180,000 of them, and now we have a strong list, which is a list of all of the weak classifiers that have been chosen, the chosen ones. Okay? And you'll notice that I pass to it the whichever one wins and the beta value, because I need the beta value to be able to calculate the alpha value, and the alpha value is the weight, how much of a vote that one should get. Okay? And I don't remember, did I implement all of the strong classifier? Did I leave any of that for you to do? Yes. So, my strong classifier class, it has a list of weak classifiers, and it has a list of alpha values for each one of those. Okay, and when I add the weak classifier, it appends the weak classifier that you pass to it onto its list, and it's going to calculate alpha given beta. And here I've just done a check because it is, if you happen to choose a very small amount of images for your training set, it might be possible that a weak classifier could get them all right. And I did have that problem, and I got a divide by 0 error. So I put in a check here that if beta is very small, make sure it doesn't go to 0. Otherwise, you could get an infinite value for alpha. And here, actually, here's the equation for alpha. It's just the log of log base, I guess natural log of 1 over beta. So it's already in there. Okay? So it adds the weak classifier onto the list and calculates the alpha. Okay? Then one of these, what you do have to implement here is you're given a list of integral images, and it's going to return the class for each of them. Okay? And so what you need to do in here relates to this equation up here. This guy right here. You have a list of T classifiers, big T class, weak classifiers. You have what those classifiers are. You have a list of them. You have the actual weak classifier there. You have a list of them, and you have the alpha values. So basically, you need to calculate this thing here. You need to sum all of that and check if it's greater than 1/2, and that will determine whether it's classifying 1 or 0. But this II is a list of integral images. So you're going to return a list for all of the different x's. You have a list of lots of little x's, and you need to return a list of what they are, what their predictions are. Okay, so that's actually the only thing that you need to implement for the strong classifier. So then here, get performance. This is once you already have a strong classifier to tell you how good it is. You pass it a list of images that you want it to check. You pass what the labels of them are. Okay, it's going to predict what it is. That's this function, this member function here. Okay, it's going to find where are the labels that are faces. Those are all the indices where they're faces, all the indices where they're not faces. Okay, then it's going to calculate a detection rate. Okay, how many of the faces are correct? Okay, the mean of checking when the predicted of all the faces is equal to 1. Okay, then what is the false positive rate? That's not how many did it get right, but rather how many did it get wrong. So it's 1 minus that. That's generally how false positive rates are given. And then, of course, correct is just the average of all of them. So this thing is returning 3 things. The overall, how much is it right overall? And then what is the detection rate? And what is the false positive rate? Okay? And you can use any combination of those things in determining when you're done training your strong classifier. Once that gets above, reaches certain thresholds of whatever you deem necessary, then you can have your loop end, the while loop end. Okay? So the only thing you need to implement here is this equation right there for the strong classifier. Okay? All right. And then after it's done, I just have it print, what the performance is. And then I go ahead and pickle dump the strong classifier so that then when you actually run the evaluation stuff, then you can get, you can just load it. Okay? All right, so the notation is the trickiest thing, okay? And sorry I confused myself there about the 2 different kinds of weights. There are the weights for the voting, and there are weights for each individual image that says how often was it correctly classified and how often was it incorrectly classified. So if it keeps getting classified correctly, its weight gets driven down and driven down and driven down and gets less and less important. You focus on the ones that are incorrectly classified. And that's the main trick of how AdaBoost works. Okay. Then we have the idea of the sliding window search. And how do we go ahead? I don't know why doesn't that show up.
Yeah, it doesn't play.
It doesn't play the one I uploaded? It used to. Why not? It did. I
found it online, but.
Well, I'll have to fix that. I was so proud of that I wasn't able to embed that you could play it. I'll have to fix it. So let's see, where do I have? Here's the. Okay. So the idea of sliding window search is, when you trained your images, okay, you were given 19 by 19, they're faces or they're not faces. Okay? When you're given an image like this, okay, it's not already neatly divided up. Okay? So the idea is you're going to take a window and you're going to slide it across there, and every position of that green window, you're going to pass that image to your strong classifier and ask, is that a face or is it not a face? Okay? So you're going to be doing many predictions with your strong classifier depending, as you move this sliding window across. So if you have a very big image with lots of faces in there, you might be doing this quite a lot. Okay? Now, what you end up with is needing to, because this image you'll need to, because also, if you, in the most general case, you're going to have a picture where there's a person that's far away from the camera and there's a person that's closer to the camera, and their faces are going to be different sizes in the image. Okay? So ideally, you would need to not only scan across the image, but you would also have to scan across the image at different scales. So if you want to detect large faces and small faces, you would need to make that. If there was someone, standing far behind her, you would need to have that green window also scan across in much smaller. And of course, the smaller the thing is, the more you have to slide it across, and the more you have to check, the more time it takes. And that's a lot what the authors of this paper were talking about. They're trying to reduce the amount of time that it takes to run the classifier. Okay? So, ideally, you would be doing this at different scales. Now, for this project, I've given you the face of me. You can choose some other person's face. You can pick whatever image that you would like to run it on. Just go ahead and include that with my in your submission. Okay, and if you want to, go ahead and do it at different scales. If you want to try, if you got some extra time and you want to play with it, run this thing across at different scales. Okay, now that image, who knows how big it is? I don't know, maybe across that face, it's definitely not 19 by 19 where her face is, okay? So every one of those images, you're going to need to resize it to be 19 by 19, okay? And I think I used OpenCV has a resize. I'm sure Matplotlib also has a resize. But basically, your image, you want to go ahead and choose it to be square, okay, because you don't want to distort it. So choose your window size to be square, and you're going to need to choose it to be about however big the face actually is in the image. So you get to cheat a little here because I'm giving you the picture of me, and you can look in that image. Let's see, in that image. In that image, I don't know, what is it from here? That's like 40 down to 100. So it looks like it's about 60 by 60. Somewhere around that range. So I'm going to take a 60 by 60 image and I'm going to make it smaller, resize it to be 19 by 19. And then the resized image is what you're then going to pass to your classifier. You also need to turn it into grayscale. So you turn it into grayscale, shrink it down to 19 by 19, okay? Or if it's smaller than 19 by 19, you need to blow it up, okay? I was going to say something, but... So that answers your question. You're going to resize the image down. Oh, that's what I was going to say. Interestingly enough, in the paper, the authors said that they don't take their images and size them down, but rather they scale their classifier. They scale their weak classifiers, where if it was a 4 by 4, if this thing was 4 by 4 pixels, and you had a 38 by 38 image, they would have it be an 8 by 8 pixels. So they recalculated their features. They changed the size of their feature rather than changing the size of the image. I'm not sure why they did that. I don't know. They said there was some sort of performance benefit, or if I remember right. It certainly is more complicated to do that. So for us, it's a lot easier just to take your large image and resize it down to 19 by 19. It's a lot easier. And right now, we're not worried about performance issues so much. Okay? Now, let me look at, just to make sure I remember right, in the rubric. That, right, in order to get those last 10 points, it needs to detect all the facial area with no false positives in that image of me, or whatever image you decide you want to pick. Okay, so that probably means that you're going to want to emphasize having low false negatives. Okay, a small number of false negatives. So in your training, you may need to emphasize that to make sure that the false negative isn't very low. Because what you'll notice as you watch the training, sometimes what will happen is that you'll get like 80% correct, and like all of the non-faces are correct, and almost none of the faces are correct. And you have 80%, because if you say it's always not a face, you're going to get 50%. So then you only need to get a few of the faces correct to bring you up to 80. 80 is actually not that great, okay? Because 50 is your baseline, okay? So you'll want to mess around with how you keep going and determine when you should be done, okay? So if you want to get full credit on this, you need to make sure there are no false positives at all. Okay. Now that's not practical in real life. Okay. To never have any false positives. And when we do the cone detection, we're going to introduce an idea of non-maximum suppression, which basically, one way to think about it is you can see all those black rectangles there. They're all individual positions of the sliding window that were said it's a face. And basically you can tell in the middle of where my face is, many of those windows are overlapping. Okay? But out here, this position right out here, there's probably only one window that is out there. Okay? And one of the things you can do is you can look at where do these detections overlap. And if there's only one or two things that overlap there, you might throw away that part. Okay, and only keep the places where it overlaps a lot. Okay, and so we'll do that sort of an idea in the next project. Okay, but for right now, you're trying to make sure you have no false positives at all. You're not going to get rid of them with this other fancier technique. Okay. All right. So that's all of. What is that? I don't even recognize that icon. Anyway. So you're going to have a single strong classifier as your result for making your decision on predictions. Okay, that's not where the authors of this article stopped. Okay, what they found is that if you needed thousands of these weak classifiers to make a classification, and you would have to run for every one of these things in this sliding window. You would need to run every one of those 2,000 things, and it got computationally intensive. You're trying to do this in real time over a large image at many different scales, etc. Okay, so they were trying to speed this up, and what they had this idea of a decision tree. Okay, and a decision tree, if we had class on Monday, we'd go more into decision trees. But basically, a decision tree is a way of sort of segmenting your search space into certain areas. It makes a lot of sense in this application that we're going to say, well, is it a face or is it not a face? You have this binary choice, but actually you can do it with regression, and you can use trees to do lots of complicated things. But basically, what they wanted is that they wanted to have, here's where you put in your image, and you're going to say, you're going to have a classifier here that may not be an optimal strong classifier. Maybe it only has 1 or 2 or 3 weak classifiers in it. Okay? But the idea is for it to always, when it says it's not a face, or when it says it is not a face, it's always not a face. So if it says it's not a face, it's always right. Okay? And so maybe it gets rid of 20% of all of the images, of the ones that are not face. And then, so in just a few computations, it can eliminate many things. So in your image, most of the image is not a face, right? So most of the time you're going across there and you're trying to see, is it a face or is it not a face? And most of the image, it's not a face. So if you have this first classifier that very quickly can discard many of the non-faces correctly, then that's pretty good. So you'll zoom across much of the image is going to be rejected very quickly. Okay? Then the next classifier maybe has more. It has more more features. Maybe it has 10 or 15 or something in it. Okay, and again, it's trying to reject things that are not faces that the first one missed. And then it's going to go again. Okay, well, if that was true, then I'm going to do another one, another strong classifier. Reject some more. And it's going to keep doing this. That's why they call it a cascading classifier, because it throws away some of them very quickly. Then the ones that it didn't throw away, it looks a little closer at them, spends a little bit more time, throws away some. Spends a little bit more time. So the faces, the ones that are actually faces, make it all the way through this tree and go through all of the levels of the cascading classifiers, the ones that are actually faces. So to classify a face, it takes a lot more time than to classify something that's not a face. And that makes sense in an image where most of it's not faces and you're only looking for the few places that are faces. So they found that was one of the big innovations. They didn't come up with AdaBoost. AdaBoost already existed. But this idea of this cascading classifier that reduced the computation time was a big deal. Okay? And so this, what's really interesting with these decision trees, they're using it in a very different way, but you can have the decision trees sort of form themselves. And it's really, you can have an automatic way of deciding, which parts of the trees are going to reject things and keep things. It can be really interesting. I personally don't like decision trees very much because it reminds me back to the whole expert system. Are you sick or are you not sick? Do you have a fever? These things that you sort of encode human information in there. There's ways to make the computer automate those decision processes, but I think there's other ways that are easier to do that and are more intuitive than with decision trees. I don't know, maybe I'm just biased and I discriminate against them. I know there's lots of people that are been very successful doing lots of things with decision trees. Okay, so if you really wanted to, you could have some extra time and you could do all sorts of extra stuff with cascading classifier. Don't worry about that. Okay, if you want to and you have lots of extra time and you want to work on an image that has faces at many scales and run it at many scales, you're welcome to do that. You just have to be careful because you're sliding that window over and it takes a lot of you have lots of different windows and you're going to have it's going to take lots of time, and you have to do that at different scales. It might actually take a fair amount of computing time to run just on one image. Okay, so have a look at that. All right. So that brings me pretty much to the end of class. We're pretty much introduced to everything now, and now it's a time of going and trying to implement everything and getting it to work. Okay? So Friday we'll meet in class. Come with your questions, and I'll field whatever questions you have. Is there anything that you already know that I've left out that you want me to cover on Friday? You don't know yet? Okay? So if you have any, if something comes up that you're struggling with, maybe email me or something, and I can prepare something to help and discuss that on Friday. Okay? All right. See you Friday.